Hello! This is a quick tutorial to talk about debugging. Well, for the most part, the tools and code provided in the PyUserCalc package should work. Sometimes things break. Often this is related to updates to the underlying code packages that themselves get updated, like NumPy. So if you run into a bug and you can't figure it out, you can, of course, always contact the developers, like through GitLab, by sending us a message. Sometimes the quick solution might be to temporarily actually downgrade your version of Python if you have a very up-to-date version and something has recently become deprecated, so it's no longer working. But it is also extremely helpful to tell us this, so we know the change has occurred. Sometimes changes are made to packages that are relatively small and we don't know, or even with bigger ones, we may not be sure of all the possible impacts on our code, and it helps to get this feedback so we know to test and push an update to the repository. The other thing that can happen is you can accidentally edit something that actually broke the code, in which case the easiest fix might be to download a fresh cloned copy from the repository. This is also why a lot of the underlying code resides in the Python driver scripts, which you probably shouldn't try to edit unless you are very familiar with Python and what the code is doing. That's these py files. This is open source code, it's licensed, and you are permitted to edit the code on your own computer as long as you give us credit for anything you use it for and publish, but there is the risk that you will break it if you edit it. However, there is another way the code can appear to break that's actually related to how ODE solvers work when they are trying to iteratively find continuous solutions to interpolated variables. Sometimes the solver just doesn't converge and cannot find a solution. This is probably the most common way the code breaks, though it's not exactly broken, really. You just gave it something that can't be solved by numerical methods in a straightforward manner. So, for example, I have a few inputs that were calculated using petrologic and thermodynamic models like p-melts for mineral modes, and then we used those modes to calculate bulk partition coefficients. But that meant that when a mineral suddenly appeared or disappeared, the partition coefficients jumped and literally made basically a right-hand turn. I'll show you one of these. In the notebook that I have set up to help with troubleshooting notebooks called the Input Smoothing Calculator tool. So I have to first load these, and then I'm going to show you in one of the input files that I had a few struggles with and had to troubleshoot. So there are just very different values in different parts of the data set. And if I actually view it, I can see, oh, there's a pretty big jump here, but then look at what happens to my radium partition coefficients at 10 kilobars. This is for G2 melting, and G2 is a eclogite, so it's possible feldspar became stable and very suddenly affected the partition coefficients for radium, for example. So when this mineral suddenly appears, the partition coefficients jumped. You also can get abrupt changes in the degree of melting sometimes. And overall, I've been pretty impressed by how well the continuous numerical solution methods can work in a lot of cases, especially considering these are very stiff models too. And so a very stiff adaptive solver routine like Radow, which we recommend using for most applications because of that property, it can do pretty well. But it can't do everything, and this one failed. When I tried to run it for disequilibrium melting in particular, where the changes in concentration are especially extreme, I was getting errors where it wouldn't solve. So what do you do? Since this is a known problem, this notebook was one I wrote to start with troubleshooting, but it may not solve everything. What this does is allow you to try manipulating values to smooth out corners, essentially, and make them more continuous and therefore potentially more solvable before you try manipulating by hand and doing a lot of trial and error. That sometimes is still necessary, but this is fast enough it can be worth a quick try. You could also just jump straight into manual editing if you prefer, and that I've always been able to make it work once I tweak the values right around an abrupt change to make them slightly smoother around the corner. But I wanted to show you this smoothing tool in case you run into this issue and would find it helpful to test. This just uses a smoothing routine to replace a few rows above and below the major breaks or changes in the input file. But for these extreme turns, like 90 degrees, it still may not work. I'm just going to warn you about that right now. But the smoothing tool can also help you attempt to locate the major break or change points and try to do this automatically and quickly test the results. So to do this, I need to know the file name in the data folder. So I can find the data file up here, and I have to put it in here. And then it'll walk through a series of ways to try to manually and automatically identify what we call change points. And it will work for both PyUser calc files that have the uranium series nuclides, or for other elements for the stable calculator tool. It doesn't really matter. It should be able to work with them all. And ultimately, what this will do is walk through a series of ways to identify and then try to automatically change the values around these change points, but you ultimately decide which points you want to actually work on, and then you will tell it to run the smoothing routine and generate a modified input file. The new file has a new name that won't overwrite the old one. The methods it suggests are first looking at this file and identifying, okay, at 10 kilobars and again at 20, I obviously have some pretty big changes. So here, I actually can manually enter those pressures in a list, and they only need to be close. Because I'll be telling it to smooth out values over a range of rows, I don't have to be exactly on the nose for those pressures, just reasonably close. So if it was 10.1, putting in 10 should still be able to find this change point. So that's fine. There's also another pair of methods below. So I'm going to save these, store them as values, and then it found the indices in this data table for where those pressures are located, so I can find them by location in the list later. The methods below will actually look for change points. So the cells I just ran find a list from, or create an array, a NumPy array from your data frame. You need an array to do some of these methods. So that's just putting them in matrix form. And then there are two different techniques set up here for looking at change points by looking at the second derivatives. So first, we're going to calculate second derivatives for all the variables. And it just tells me the sizes of the arrays. I don't really worry about those too much. I have lots of different variables in there, so I'm going to have a bunch of different numbers. Then, this list is telling me where the second derivatives are especially large and where they're located. The next routine will look for peaks using a peak finding routine, and I only get a couple of those. Now, the next cell should plot the results with the index value, and it plots them both together. Now, in pressure, there's not going to be a change. It's just automatically gathering every column from the input file. So pressure is changing continuously with depth. These change points are not being located there. They're being located in some of these other files. I also didn't change KR, the permeability, which I have in this, this input file. It plots it, but it's obviously not where there are big breaks. Now F, there's a bit of a change, but these are pretty subtle. So my guess is they're being located elsewhere. Aha, it found this big change in uranium. It also found some others in thorium, and it found the big change in radium. This is encouraging. Now, some of these other data points are probably, say, simple inflections, gradual changes in curvature that show up in the second derivative, but are not actually major breakpoints or change points. So I don't actually want to bother smoothing around those. I would like to smooth around this one, however, and that's around 575 or something like that. So now I need a list of all of the things I have actually determined. So I'm going to make a list of all of the change points and put them into one consolidated list. That makes it a lot easier to work with. Now, some of these, like 475 and 478, may actually be the same change, just seen over a few different rows, and the peak finding routine has a bit of width on that peak, depending on which variable you look at. I wouldn't actually want to smooth at both 475 and 478. The other thing I can do is manually decide which of these points I actually think look convincing. And it's helpful here to go back up to the plots and say, okay, the 575-ish one, 578, I guess, that one I think is real. So I'm going to put 578 in this list. There's also this big break at 470 something seen in uranium. So that's either the 475 or 478. It's possible it's both of them. So I'm going to put that one here as well as one I think is actually significant. So I'm just saving that and confirming that those two values in particular out of this list I think are important. Now I have a choice. I have 3 lists I have generated. I have generated a manual list by looking at the simple plot at the very beginning of this notebook. I have also selected values, so I've kind of curated a list from the automatically determined one, and then I have the automatic one, auto. I'm going to use this curated one this time, but you can choose any of these. Most of the time, auto is going to include some values that probably you don't need to smooth over. That said, smoothing over them may have almost no effect, so it might be relatively harmless. But I lean towards usually focusing on just a few very obvious breaks, at least for my first round of smoothing. So I'm going to do manual and selected, or selected. And in this case, I'm going to use this selected or curated list. So this is the list I want to smooth over. The other thing I can do is say I wasn't sure if 475 or 478 were the most important value, and I put them both in here, but it turns out they're so close together that it actually will be within the same set of rows used for smoothing out that corner. The next cell will make sure you don't have any duplicates. This would also be relevant if you decided to use the whole automatically generated list. So it will choose either of the two values if they're that close, and your smoothing routine should encompass them both. So in this case, it doesn't make a difference because I've already selected two values that are quite far apart. The rest of this routine or calculator tool is set up to do the smoothing. You tell it a p lambda value, which tells it kind of how to smooth over your interval, like how sharp to make it versus how smooth to make it. And then you also give it the number of rows over which you want to cause the smoothing to be recalculated and replace the original rows for all of your values. Depending on the resolution of your input file, this may be a very large number or a very small one. Mine has very fine resolution. It has hundreds of rows when you go up to this data table, 656 rows, just to get this resolution over 70 kilobars. So if I only do a few rows, I'm not going to smooth over a very big interval and it will still be quite sharp. Whereas if I had a very coarse resolution, large pressure steps, I would probably want to use fewer rows, or I would smooth the whole thing and it wouldn't be close enough to the thing I want to test. So I'm going to make it 20. That's fairly large, but because of my high resolution, it might actually turn out to not be that large. I'm going to generate a new data frame that doesn't overwrite my original one. And it looks like this. Okay, so this is the one where I'm going to impose changes. The next cell actually calculates the smoothed results. Now I can't really see them here because they're all buried in this extended data table, and it's also hard to look at in a data table. So I want to see what it looks like in my smoothed result. It's hard to see in the green. And the green, like I said, might actually be so sharp that it's not possible for a smoothing routine to do enough, and you do need to go in and do some manual changes. This is looking fairly smoothed out, however, so it does work on more gradual changes like this. If I didn't have this big change in radium partition coefficients, just the big change in uranium, and that was still causing problems, this might be enough that I would be able to recalculate it. And then you want to save your smoothed data table using a new name. So it will be whatever your old name was _ smoothed. And you'll be able to now test that in your melting model. As I mentioned above, if it's not enough, you probably will find it helpful to open your CSV and manually edit some of the values close to the abrupt change, and then look at the figure in User Calc. You can even use this notebook just for viewing it and see if it looks better to you. And then you can always do test runs in User Calc and see if it accepts it. Happy calculating.